Okay, so hi, my name is Dr. Nick Longridge. I am a paleontologist and evolutionary biologist. I describe and name dinosaurs among other things. And today I'm going to talk about a dinosaur that I described and named. The title of today's presentation is A Giant Tyrannosaur from the Campanian Maastrichtian of Southern North America and the Evolution of Tyrannosaurian Gigantism. It's based on a paper by Sebastian Delman et al. With me way down the list on the et als. So this is a project I was lucky enough to be involved in, collaborate with these guys recently on describing a new species of Tyrannosaurus, which is something that doesn't happen every day or even all that often. So to summarize what I'm going to talk about here today, we studied a giant Tyrannosaur from the late Cretaceous of New Mexico. This is an animal that was previously referred to Tyrannosaurus rex. It turns out to be substantially older. We're not sure exactly how old, but quite a bit older than T-Rex, we think. And critically, the anatomy is inconsistent with T-Rex, with any known T-Rex specimen. It appears to represent something different, something more primitive. And why does this matter? Why is this cool? It pushes Tyrannosaurs back in time. It's not a T-Rex. It's just as big as a T-Rex. And it shows that these animals are not coming from Asia, that Tyrannosaurus is coming from southern Laramidia, that is the southern part of the North American continent. That's where they're evolving, and they're later dispersing north. And then just general implications. What does this mean for paleontology? I've made this argument before, but I'm going to make it again. Fossils assigned to Tyrannosaurus rex may include multiple species and genera, and we may be underestimating the diversity of dinosaurs, and that fossils are maybe it's really hard to distinguish species. We may be underestimating just how many things are in T-Rex and a lot of other stuff out there. So, the problem. Where does T-Rex come from? It is among the last and the largest of the Tyrannosauridae. These are giant predatory dinosaurs that dominated the end of the Cretaceous period. And T-Rex appears suddenly around 66 to 67 million years ago in the latest Maastrichtian of the Western interior. So like the Hell Creek Formation of Montana and the Dakotas, the Lance Formation, Wyoming, the Frenchman Formation, Saskatchewan, the Scollard Formation of Alberta. It suddenly shows up, and we have nothing like it known from lower down in these beds. So if you go out to Montana or Alberta, you don't see anything like T-Rex. You see in the Horseshoe Canyon Formation, you have Albertosaurus, it vanishes, T-Rex shows up. Where is this animal coming from? And this has been an ongoing debate. Is it evolving somewhere in North America where we just hadn't looked before? If so, why are we not seeing the fossils? Or is this thing potentially coming from Asia across the Bering Land Bridge? So up until this point, the closest known relative of T-Rex is this animal called Tarbosaurus. It was known from Asia, so it seemed possible that maybe Tyrannosaurus and Tyrannosaurus rex are coming in from Asia. But we didn't really know. Now, the answer to this comes from a formation called the Hall Lake Formation. This is a series of late Cretaceous terrestrial beds. This is, I believe, I want to say paleo-environment. I think it's a tropical rainforest inland environment. And it's out in western New Mexico. And it outcrops around this reservoir called the Elephant Butte Reservoir. It's about maybe an hour and a half away from the Trinity test site, the atomic bomb test site, and about the same distance from White Sands National Monument. So it's kind of out in the middle of nowhere. There's not a heck of a lot of exposure out there. But there is some Cretaceous terrestrial out there, and it's not super rich in bones, but there are bones in this horizon, and it's been prospected on and off for over a century. People have been going out there and finding bones. And in that time, we've slowly put together a picture of what the Hall Lake Dinosaur Formation fauna looks like. And it has a giant Tyrannosaur, it has a large horned dinosaur, it has a big hadrosaur, it has a Titanosaur, a Lamosaurus, or something similar to that. And this was originally thought to be kind of a classic late Maastrichtian fauna, or what you would call a Lancian fauna, that is corresponding to the fauna we see in the Lance Formation at the very end of the Cretaceous in Wyoming and nearby in Montana. So this was thought to be a Lancian fauna. T-Rex, Torosaurus, unnamed hadrosaur known from big thigh bone, a Lamosaurus or something similar to that. Turns out to be a little more complicated than that when you dive into it. And so why did we decide to re-examine this? Well, it went back to this animal here. This is the Hall Lake Torosaurus, or it was thought to be a Torosaurus. So the Hall Lake Torosaurus consists of a partial skull. We have the parietal, we have the jugal, we have the postorbital, the horns, some other bones from the skull. And it was originally assumed to be a Torosaurus. So it's got big holes in the frill, has the apertures, openings, windows carved into the frill, and Triceratops has a solid frill. So it's not a Triceratops, clearly. But that doesn't make it a Torosaurus, because those holes in the frill will almost everything that isn't Triceratops has that. So it doesn't by default make this Torosaurus. And going back and looking at this animal, it turned out it was probably something quite different. So Torosaurus has this very wide kind of arched frill. This thing has a much flatter frill, kind of a V-shaped caudal margin. It's not nearly as wide. And the key thing here is the parietal midline bar. This is very, very diagnostic for horned dinosaurs. Torosaurus has a very characteristic parietal midline bar, the midline bar, that frill that separates the fenestrae. And it's very broad, and it's kind of, got a shallow peak, like a roof with a very low pitch. Very broad bar. This looks nothing like that. So it's got a very narrow midline bar, reduced down, it looks like a bar, and it's kind of arched dorsoventrally, so it's got this rod-like shape. So this is clearly not a Torosaurus. So what is this animal that's coming from the Hall Lake Formation, if not Torosaurus? And it turns out to be a new species, something we ended up naming Sierraceratops turneri. And this is our reconstruction of what we think this animal would have looked like. What's it related to? Well, our best guess is that this animal is related to a couple of other animals known from the Southwest. One of these is an animal called Quahilaceratops from, helpfully enough, Quahila down in Mexico, in northern Mexico. And that is known from the latest Campanian of Mexico. And the other animals related to is an animal called Bravoceratops from the early Maastrichtian of Texas. So it's something different. It's not related to Triceratops. It's not related to Torosaurus. It's a separate lineage. And this was, for me, pretty exciting. I'd worked on horned dinosaurs before, worked on late Maastrichtian dinosaurs before, and here we had what seemed to be a distinct lineage of horned dinosaur surviving up into the late Maastrichtian. So this is increasing, it appeared, the diversity of horned dinosaurs at the very end of the Cretaceous period, which has implications for understanding how diverse dinosaurs were or weren't when the Chicxulub impact happened, when an asteroid came down. There's a lot of species or few. And this seemed to up the diversity at the very end. Anyway, that was the story we were interested in telling, that there's like this other thing out there in the late Maastrichtian. But here's kind of the catch is this really late Maastrichtian? And often one of the hardest things to do as a scientist is, like, you've got this really cool story, and sometimes you have to step back and be a bit skeptical and say, yeah, but really, is this really what we got? And you just double check it, and kind of you have to be your own worst critic. And when you have a really cool story, you have to say, yeah, but is this too good to be true? And the thing I started wondering is, like, okay, but is this really late Maastrichtian or not? It's clearly not a Torosaurus. It's clearly something new. That part's new, but does this late Maastrichtian part of the story hold up? So I started asking around, like, well, why do we think it's late Maastrichtian? Well, it's late Maastrichtian because it has Torosaurus in there, and well, but this isn't a Torosaurus. And then, like, well, like, I'm like, well, what are the radiometric dates doing? And Spencer Lucas told me, yeah, there's some radiometric dates, and they're like Campanian, but we don't buy them. And like, I'm like, wait, what? Like, the thing about radiometric dates is they're not perfect, but they're pretty good. They can be off by maybe 1 million years sometimes, maybe a bit more, but they're typically not off by, many millions of years. And so that really kind of got my attention when I learned that the radiometric dates were not consistent with the late Maastrichtian age. I was like, well, wait, how old is this thing, this new animal that we're discovering here, the Sierraceratops? And if you look at the stratigraphy, it's pretty interesting what's going on here. So fairly far up in section, we have a Titanosaur. Now that animal has to be at least 66 million years ago, is that date. Why is that? Well, because dinosaurs go out at 66. You can't have a dinosaur in the Paleocene at 65. So this dinosaur, that's got to be at the very minimum. That can be no younger than the KT boundary, or what's currently KPG boundary, at 66. It's probably not any older than Maastrichtian. It's probably not Campanian, because at least so far we don't have any Campanian Titanosaurs. So this is probably, somewhere between, it's like 66 and 72.1 or whatever the Campanian Maastrichtian boundary is for the Titanosaur up there. Then below the fossils, we have the horned dinosaur, Sierraceratops, and our Tyrannosaur just above that, which we'll get to. We have a series of dates. So we have 73.2, we have 75.2, we have 74.9, 75.0. These are all Campanian dates. These are millions of years older than the late Maastrichtian. Now, could there be some problems, some errors here? Yeah, potentially. You look here, you go 73, 75, 74. what's wrong with this picture? Well, one of these, you have an older date above a younger date. So clearly something's wrong there. Probably the 75.2, which has these big errors on it, is probably off, and it's probably somewhere between 74.9 and 73.2. But consistently have 4 different dates, and they're all Campanian. It is unlikely they're all wrong. And then not far above that, we have our horned dinosaur and we have our Tyrannosaur. So, we don't, ideally what we'd want is radiometric date above those things. We don't really have that, but it's very difficult to see a scenario in which these things can be late Maastrichtian. You've got 2 million years of rock that are, late Campanian, spanning about 75 up to 73. Then you have a small amount of rock there. And unless you're depositing millions of years there, very rapidly depositing a small amount of sediment, your Tyrannosaur, and then really slow down your deposition, go up to that Titanosaur, under a number of different assumptions about depositional rates, you're probably looking at something on the order of maybe 71 million years ago up to about 73 million years ago. This is well below, 66 to 67, where you would expect to see Tyrannosaurus rex. So what's going on here? This thing is millions of years older than we expect if it is, in fact, a Tyrannosaurus rex. So what do we actually have of this animal? Not a heck of a lot of it. This is the Hall Lake Formation Tyrannosaur. Here it is on display in the museum in New Mexico in Albuquerque. Originally, it was discovered back in the early 80s and excavated. It was found by a couple people hiking around the, around the Elephant Butte Reservoir. Dave Gillette dug it up in 1983 and collected 3 bones, a dentary, a prearticular, and a palatine. So what is this thing exactly? And first of all, what is it? It's big. I mean, you can see my hand there for scale. This is a very, very large animal. How big is it? I think the dentary it's one of the longer T-Rex dentaries, although it's quite slender, so it might not necessarily correspond to, a super huge animal, but I think it's somewhat longer than the holotype of T-Rex, the Carnegie Museum 9380. I don't think it's quite as big as Sue, so it's probably not one of the biggest T-Rexes, but it's probably comparable to your average T-Rex in size. It's very, very large, and I mean, that's one reason everyone was so happy to call this thing Tyrannosaurus rex for so long. It's huge. Nothing else was known to get as big as T-Rex, so it kind of made sense. But there are a number of features that kind of hinted that this thing was something different. And so Sebastian and some of the other guys in the paper were looking at this thing and saying, this is different. And going and looking at it, I agreed with them, yeah, this does not look like a T-Rex. The really striking thing is just the shape of the jaw. You can see it's very bowed. T-Rexes typically don't have that bowed shape. It's very upturned at the back and quite shallow in the back of the jaw. And nothing else quite looks like this. It was, however, identified as a T-Rex by Gillette back in a paper in 86. But Lehman and Carpenter looked at it in 1990 and said, this is a new genus. This is something distinct. And then Carr and Williamson looked at it in 2001 and again called it a T-Rex. And pretty much for 20 years, everybody was happy to call it that. And that's kind of where it stayed until we kind of came in here and said, hey, let's take another look at this thing. And again, it was just, we had no intention of, or at least I had no intention of kind of revising this animal. And it was just the ceratopsian that kind of made me realize that, these guys were onto something and we had something very different than T-Rex here potentially. So fortunately, we have a number of other elements that turned up. These were dug up a few years later after the original stuff was recovered. The site was revisited by Williamson, and he found a number of other elements. So in addition to the dentary, the prearticular, and the palatine found by Gillette, we have additional elements including a postorbital, a squamosal, an angular, and an articular. This might not sound like a heck of a lot. I mean, it's pretty far off of a complete skull, but often these skull elements are incredibly diagnostic. They show subtle variations from species to species. You can infer a lot about what's going on with the skull because each skull bone is contacting multiple other skull bones. So you have its anatomy, it also has contacts with these other bones. So pretty much every single bone in the skull is diagnostic. Now, you might not want to name, an entire Tyrannosaur species off one skull bone, but we have a whole series of skull bones. You can actually get a pretty good idea of what the anatomy is like, and in particular, what this animal, what it is. And if every single bone is telling you the same story, you can be pretty confident in your story. So what we found was that this animal is very similar to T-Rex overall, but there are these subtle differences, and the key thing is there are subtle differences in every single bone. And because T-Rex is, unlike a lot of other dinosaurs, known from a lot of different specimens, we have a lot of T-Rexes to compare against. So we can take each bone, compare it against all the T-Rexes, and we can do that bone by bone by bone, and we can show that for each one of these elements, it is different. It lies outside the range of variation known for Tyrannosaurus as a whole. That this is a distinct outlier in every single skeletal element. And that's why we're pretty confident that this is a new species. This is not just some subtle individual variation or just an outlier of T-Rex. This is something entirely different than T-Rex. So we can go through these bones, bone by bone. I could spend a lot of time on this. It would probably bore you to tears. But just to kind of briefly survey some of the differences and show you, yeah, these things are different. The postorbital is different. The front end of the postorbital kind of projects forwards. It hooks downwards more strongly. In your typical T-Rex, this thing projects forwards. The shape of the boss on the postorbital is different. It's lower and further back. In T-Rex, it tends to be higher. It's further forward. So we have these distinct features of the postorbital anatomy that lies outside the range of variation we see in T-Rex. If you look at the squamosal, again, this bone is different. The ventral process, the one with contact, the quadratic jugal, is very strongly projected downwards. It's hooked more forwards in T-Rex, so it's different in that morphology. If you look at the underside of the squamosal, this is where you see a lot of differences. So you have the squamosal fossa, this pneumatic fossa, excavating the underside of this bone, and there's a bar of bone across the anterior end of that fossa, forming the border in the elephant butte tyrannosaur. And this bar of bone is absent in T-Rex. There's kind of a low, broad ridge there. So this is completely different than anything we've seen in T-Rex before. The medial margin of that bone is quite strongly bowed in this animal. It's much straighter in a T-Rex. So again, here's another couple of features in this bone that are inconsistent with what we've seen in T-Rex before. Moving on, the splenial has a number of differences. The apex of the splenial is more far forward. The posterior process of the squamosal projects more posteriorly, less posterior-ventrally. That's associated with the overall change in the shape that we see in the mandible with the dentary. There's this little shelf of bone that would contact the dentary that we don't see in T-Rex. So this bone is distinct as well. Moving on, the prearticular, you can see it's very strongly bowed in T-Rex. They're all kind of hockey stick shaped. This thing is more subtly bowed like a boomerang. And it has this articulation for the angular bone that is much more weakly developed than what we see in T-Rex. So we have this very weak articulation here. And so again, this is distinct. If you look at the angular, this is also different. It has this little articular face there. It's quite reduced. It's big in T-Rex. And this anterior process, the bone, tends to be much more strongly hooked in T-Rex. So we have a series of subtle differences in all these bones. There's a couple of bones I haven't even talked about here yet, like the articular. It's again, this might, yeah, this stuff is really technical. My point is not that I want everyone to necessarily understand this. I have trouble even keeping all these characters straight myself and have to go back and look at the literature carefully to understand it. But it's just like there's a lot of little details in there that tell you that this thing is a T-Rex. We have a whole bunch of T-Rexes we can compare to, and it's distinct in every single bone. Every bone in the skull has at least a couple of differences. So the devil's advocate might say, okay, yeah, but these differences are really subtle. To which I would say, well, so what? The differences between species are often subtle. The differences between genera are often subtle. So here you can see, for example, we have two different skulls of two different Tyrannosaurs. One of these is a T-Rex. The other is Tarbosaurus batar from Mongolia. You know, if I switch these around, could you tell which was which at a glance? And even a lot of experts, I mean, some experts might actually recognize, oh, okay, that's that skull from Mongolia, but just generally speaking, the anatomy, at first glance, they're pretty darn similar. And offhand, because I spent all my time comparing this thing to T-Rex and didn't spend nearly as much time with Tarbosaurus, I actually have trouble picking out the distinctive features of Tarbosaurus in these photos. It's that similar. So there are differences, but they're subtle. It is not unexpected to have subtle differences between different species or even different genera. The thing is in taxonomy is not whether differences are subtle or not, it is whether they're consistent or not. So if you look at, okay, so for example, two species, Homo sapiens and Homo neanderthalensis, the Neanderthals. The differences between us are quite subtle. We have a prominent chin, they have a weak chin. We have a flat forehead, they have a big brow ridge here. We have a bulbous skull, they have a more elongate one. These are actually pretty subtle. We don't look that different, but they're consistent. Every single Neanderthal has the big brow ridges. Every single Neanderthal has the weak chin. Every single Homo sapiens, or almost every single one, has quite a strong chin. So they're very, very consistent. You can look at hundreds of Neanderthals, hundreds of humans, and these little differences are consistently found in one population, not the other. So that's how you have to do taxonomy. And obviously this can be difficult when you don't have a very large sample size. So to look at this animal, we threw this thing into a phylogeny. We coded up all these characters into a matrix, reduced them down to ones and zeros and twos. The computer could process. It tries to find the simplest arrangement of these of branching between these various species to account for these character differences, and it spits out an evolutionary tree. And we get this thing related to T-Rex. That might seem obvious in retrospect. At the time, we were actually not entirely certain this thing was related to T-Rex. We thought maybe it's related to Tarbosaurus, but we found a few subtle features in the lower jaw, the reduced tooth count, that seemed to kick it over closer to Tyrannosaurus. So, I mean, that's kind of another thing to keep in mind here. We actually struggled to find features that made this thing definitively a T-Rex. There were so many differences and relatively few features it shares with T-Rex that aren't seen in, say, Tarbosaurus. But we found a couple, and that seems to kick it over towards T-Rex. We also did a more sophisticated analysis where we incorporated stratigraphic data, like where these things are distributed in time. This kind of helps you produce a slightly better resolved and more accurate tree. At least we hope it does. Phylogenetics is a bit of a dark art. Are we doing it right? You add some more specimens, change a few codings, get a slightly different arrangement. But we think we're probably pretty close to what's pretty close to the actual scenario for Tyrannosaur evolution here. And the key thing here is that with these branch lengths of knowing when things are appearing and how long they're separated in terms of evolutionary time, we can get more accurate reconstructions of biogeography. So we try to map biogeography onto this tree and reconstruct not just when these things are evolving, but where they're evolving. Unsurprisingly, we find Tyrannosauridae as a whole is coming out of North America. So we have the Albertosaurians, things like Daspletosaurus there, Tyrannosaurus, et cetera, and we have one little side branch that goes off and produces Tarbosaurus. What we find that's kind of interesting here is that there seems to be a major radiation of the Tyrannosaurines, that is the Tyrannosaurus-like group, that is in the American Southwest. So we have a whole series of southwestern taxa, things like Teratophonius, Bistaheversor, Lithronex, that are kind of marching up the tree towards our New Mexican Tyrannosaur and Tyrannosaurus rex. The implication here is that the ancestors of Tyrannosaurus and this early Tyrannosaurus species are found in the Southwest, and later when Tyrannosaurus rex shows up in Montana and Wyoming, it's coming from the Southwest. It seems to show up out of nowhere. It's not showing up out of nowhere. It's showing up out of the southwestern part of the continent. So what are the implications here? I think there are some really potentially very interesting biogeographic implications to this. We have a lot of big things down south, and a lot of these big things show up there surprisingly early when the northern parts of the continent are dominated by much smaller dinosaurs. So one of these southern giants that we have is an animal called Titanoceratops that I described a few years ago. Titanoceratops, it's like a Triceratops, but more primitive. It might even be the ancestor of Triceratops. It's substantially older, something like 74 million years old, but it's just as big. And it implies these giant Triceratops-like dinosaurs, the Triceratopsins that give rise to Triceratops and Torosaurus, are evolving in the southwest and later moving north, just like Tyrannosaurus does. It's evolving in the southwest and then moving up north towards Montana and Wyoming and Alberta. Another giant dinosaur that we have in the southwest or in the southern part of the continent is Magnapolia from Baja California. So Magnapolia is a giant duck-billed dinosaur. It is among, if not the largest duck-billed dinosaurs in North America and one of the largest duck-billed dinosaurs known. And this thing is found down in Mexico. This particular lineage does not go up north. And then we have a Lamosaurus, this Titanosaur. These things, again, are restricted to the southern part of the continent. The furthest north they get, at the very end of the Maastrichtian, and they show up in Utah, but they do not get further north into Montana or Wyoming. We've never found even so much of a tooth of one of these animals up there. So they're clearly restricted to the south. So it kind of looks like the south is this place where large dinosaurs tend to evolve. Some of them move north, some of them are stuck in the south. And then if you go really far north, up to the north slope of Alaska, you've got these fairly small tyrannosaurs. And you have this thing, Nanoxaurus is very small bodied. We have these small admonosaurs. It kind of looks like what we might have. This is a bit speculative. I could be wrong. I think it's an interesting hypothesis to test. I think what we may have is an inverse Bergmann's rule, which might not make a lot of sense if you don't know what Bergmann's rule is. But what Bergmann's rule is, it's an hypothesis about biogeography that as you move away from the equator towards higher latitude assemblages, you tend to get larger animals. And it's a bit debated, but it seems that mammals follow this rule. Dinosaurs might be doing the opposite. It may be that instead of getting bigger as you move away from the equator, as you move from low latitudes to high latitudes, you might be getting smaller dinosaurs. And the southern latitudes where the big things tend to emerge and they tend to stay down there. And again, could be wrong about this. We don't have a heck of a lot of dinosaur species to test this hypothesis with. There's a lot of missing data, but I think it's an interesting idea and worth throwing out there. And is it just a coincidence that we keep finding these ancestors, these giants, things like Titanoceratops, things like this New Mexico Tyrannosaur down south? Maybe not. Maybe that's where they tend to evolve. So the next question is just how many species is T-Rex? This is, I think, a really interesting problem. So if you look at Tyrannosaurus rex, it has a very short, deep maxilla, and there are other specimens. Specimens have been identified as this Tyrannosaurus imperator that differ. They have a longer, lower maxilla. Another way in which these animals differ is you've got a very straight squamosal in the holotype of T-Rex. The squamosal tends to be highly bowed. In this animal, 5027, which may represent a T imperator, this other species that's been proposed. The lacrimal is different. It's very L-shaped in Tyrannosaurus rex. It's kind of more shaped like a 7, kind of more hooked in 5027. The chin is different. In T-Rex, you have this very deep, massive chin. You have a weak chin in 5027. Again, are these differences meaningful? Well, if you look at like humans, the difference in chin shape is meaningful. We have quite a prominent chin. Neanderthals have a weak one. So these animals are, I would suggest, at least as different as Homo sapiens and Homo neanderthalensis. I think it's entirely plausible that we've got two species of Tyrannosaurus in the latest Maastrichtian. That being said, I think this needs a lot more careful study. We need to look at more specimens, look at the stratigraphic distribution, see if these characters tend to correlate and track one another. That would be another indication we have two separate species, is these guys have one suite of features and then a completely different set of features is found in this other thing. So maybe, maybe not. A third species that's been proposed, this Tyrannosaurus regina, I'm a little more skeptical of that. I can buy two species, three species feels like a bit of a stretch to me, but hey, we need to look at it. It's not impossible. Okay, so moving on, another potential species of Tyrannosaurus is this animal that has not yet been named from the Havalina Formation. First of all, it's quite a bit older than Tyrannosaurus rex. So it might be mid-Maastrichtian and maybe a couple million years older. So just on that basis alone, dinosaur species don't last that long. It's quite likely to be something different. But then if you start looking at the anatomy, you see a number of features that are distinct from Tyrannosaurus rex. The anterior part of the maxilla is quite short. You have this very short anterior piece, part of the maxilla ahead of the anterorbital fossa. It's much more elongate in T-Rex. If you look at the width of the anterorbital fenestra, or the accessory anterorbital fenestra, there's a lot of technicality, all these names, the anatomy, but the accessory anterorbital fenestra is quite a bit longer in this animal, and it's not as elongate in T-Rex. And then you have the ascending process of the maxilla is coming up much more steeply in this animal, and it's kind of sticking backwards a bit more in T-Rex. This thing seems to have a different skull shape. I think it is entirely plausible that this is a distinct species. It's older, and the anatomy is quite a bit different. Then we have the Nanotyrannus problem, one of the biggest debates in paleontology. This is an ongoing debate about these small Tyrannosaur skulls from the end of the Maastrichtian. Are these things a distinct species, a distinct genus, or are they just juvenile T-Rexes? There's been a lot of argument about this, and it has sometimes been treated as like, oh, they're definitively young T-Rexes, and it's just like this crazy idea, this almost conspiracy theory that they could be anything else. The consensus is known, the experts have spoken, this is just T-Rex. I beg to differ. I've got another presentation on that, which you're welcome to take a look at, but I think these things are something different. First of all, we've got these small Nanotyrannus specimens. We've got these big T-Rex specimens. If one turns into the other, we should have fossils capturing that transition, intermediates between the two. They don't exist. There is nothing that combines features of Nanotyrannus and T-Rex. That seems to argue these are not just a growth series, but they're distinct species, these kinds of discrete clouds of variation. Another problem is that if you look at the growth series, we do know for a good growth series for Tarbosaurus over in Mongolia, baby Tarbosaurus look nothing like Nanotyrannus. So either T-Rex grows in a radically different way than its closest relative, it's got a completely different developmental pathway, or these things are not really juvenile T-Rexes. The biggest issue here, however, is that for Nanotyrannus to be a juvenile T-Rex, it has to be a juvenile. And people have chopped open these bones, they've looked at the growth rings, and I'm going to argue that the growth patterns here we see are inconsistent with these things being juveniles. They can't be juvenile T-Rexes. So if you look at the inside of the bone, the growth rings are quite closely spaced in the middle of the bone. And as you move towards the outside of the bone, they get even more closely spaced. So it's not growing all that rapidly. You have to grow pretty quickly if you're going to grow up into a T-Rex in less than 100 years. And then they start growing more slowly. The growth is decelerating, like these things are basically reaching full size or close to full size. So these things appear to be pretty mature. They're either subadults or young adults. That is, they've reached full size, almost full size, and growth is now slowing. So this seems to be something different. Within the Nanotyrannus specimens themselves, there's quite a bit of variation. Maybe there's more than one species in there. Then there's this animal. This is an unusual skull. It's quite fragmentary. It shows a lot of features that are shared with Nanotyrannus, but it also shows some interesting differences. So the antorbital fossa has this very triangular, narrow shape, unlike a broader, more U-shaped one in Nanotyrannus. The end of the maxilla is quite long and narrow. This is has a very longer rostrine skull, has a very long, narrow skull like a greyhound or like Alioramus from Mongolia. And then the lower jaw is quite distinct. It has a very slender lower jaw, and the tip of that lower jaw is upturned. The chin is a different shape. Is that significant? Well, again, Homo sapiens, Homo neanderthalensis, the chin shape is significant. These differences, they have functional significances in how these skulls are probably used and the type of loads they could bear when they're biting. They are probably working somewhat different. And again, if you look at birds, one of the distinguishing features of a lot of bird species is beak shape. Why is that? Because different species eat different things. That's how they keep out of each other's way, niche partitioning. Darwin's finches, different beak shapes. So these subtle differences in jaw shape are indicative of different diets and different species, I would suggest. There might be a lot of things currently lumped into T-Rex. So just how many things do we have? That's a good question. So I think there's two valid species at least. There's Tyrannosaurus rex and the new one from New Mexico that we are now naming Tyrannosaurus macraensis after the McRae group that contains the Hall Lake Formation this thing came out of. So we've got two Tyrannosaurus species. There are a number of things that I suspect are invalid or likely invalid. So there's a metatarsal called Ornithomimus grandis. I think it was that Marsh thought it looked like Ornithomimus, but really big. It's Tyrannosaur, but it's just a foot bone. It's not really diagnostic. That's not a valid species. Manospondylus gigas is a couple of vertebrae. I want to say it was that Cope that described those. I forget. Anyway, but Manospondylus, just a couple of vertebrae. That's not diagnostic. That's an invalid taxon. Dynamasaurus imperiosus, named by Osborne in the same paper, he names T-Rex. That just turns out to be another T-Rex. That's not valid. Dinotyrannus megagracilis, probably not valid. Tyrannosaurus regina, probably not valid. I could be wrong. Maybe more fossils will turn up. Possibly valid, something like 4 or 5 species maybe. So Tyrannosaurus imperator, I think there's a very good chance that's valid. I just think we need to work on that more and kind of figure out what specimens, what characters diagnose it and what specimens have what characters and kind of sort that variation out a little more clearly, especially with respect to stratigraphy. The Havalina formation Tyrannosaurus, I think, is very likely to turn out to be something distinct. Nanotyrannus lancensis, distinct. Is there another Nanotyrannus in that? Possibly. And then there's this thing Stygivenator, which I think might be distinct from Nanotyrannus. So possibly when all is said and done, the things we currently call T-Rex could end up being, 5, 6, 7 species. It's not inconceivable. I think we're going to end up with more than just 2. But there's a lot of variation there, and I think there's more variation than you expect for just a single species. So I think what it comes down to is that diagnosing species is really hard. Now, think about modern birds. Is that a good analogy? Well, they're dinosaurs. Birds are living dinosaurs. They descend directly from the theropod dinosaurs. So I think they're a pretty good analogy. Maybe not perfect. But if you look at, say, a couple of closely related species like a crow and a raven, how do you distinguish them? They're distinguished by features that are often quite subtle, differences in size, difference in beak shape, or differences that don't preserve. So how do you diagnose these two things? You're out in the field, you see a black bird. What is it? Well, okay, the raven is diagnosed by, it has relatively large size, it has a big beak, it has these very long, relatively slender wings with long slots in the tips of the wingtips, it has a wedge-shaped tail, it has these elaborate throat feathers, it has a hoarse croaking call, it hangs out in relatively small social groups, and it likes to soar a lot, has soaring flight. Crows, meanwhile, tend to be smaller. They have a shorter, straighter beak. Their tail does not have that wedge shape to the tip. Their wings are weakly slotted and not as elongate. They lack those big throat feathers. They caw rather than croak. They hang out in great big social groups, murders of crows, and they tend to flap a lot and soar relatively little. So think about these ways that a birder might use to distinguish a crow and a raven in the field. How many of these observations, these diagnostic features, are accessible to the paleontologist? It is entirely possible different tyrannosaurs had different culls. We'll never know. Did they have different colors? Quite likely, we'll never know. What do we have to work with? I mean, if you think of what would happen if, for example, if crows and ravens were extinct and you took a paleontologist and you handed them a few fossils, how accurately do you think they'd be able to distinguish what was going on there? Maybe you give them one raven skull and you give them a dozen crow skulls, but most of the crow skulls are either crushed or fragmentary. Would they be able to recognize they had two different species there? And quite likely they'd look at this and say, oh, this is all one species. This is intraspecific variation, or these variations here could be, sexual dimorphism, or it's just individual variation. This big one has a big beak. It's not meaningful. Are we doing something similar with fossils? I think it is entirely possible. I'm not saying individual variation doesn't exist. I'm not saying sexual dimorphism doesn't exist. I'm not saying these things aren't important. What I'm saying is species are really, really hard to tell apart. And what we call a species in the fossil record could actually be clusters of closely related things that we were having trouble distinguishing because we just don't have a sufficient sample size to see what the range of variation is and to really tease these things apart. So this raises an interesting question. Are we underestimating diversity? T-Rex is very, very well studied, but it might well be that what we think is traditionally thought of as one species is a lot of species. Does that extend to the rest of the Dinosauria? If you look back through the history of paleontology, Marsh and Cope were very, very aggressive in naming species and probably named way too many. I think I've lost track of how many times Triceratops was named, like a dozen times, 15 times, 20 times. I literally can't keep track of it all. I forget. But it was a lot of times. And I guarantee you there's not that many species of Triceratops. 2, sure. 3, maybe, wouldn't surprise me. Maybe there's 4 for all I know. I don't think there's 20 species of Triceratops. And these guys were pretty aggressive. They were naming incomplete stuff based on fragmentary, just little subtle differences and that weren't necessarily consistent differences. And probably a lot of this was driven by ego and jealousy. They were in competition and each one wanted to name more dinosaurs than the other. Was this best practice or even good practice? Probably not. But the pendulum may have swung too far in the other direction, where you started lumping together a whole bunch of different things that had different morphologies, that were found in different formations, different times, different places, where it's less likely that they might be the same species. If you're finding things very far apart or they're from different times, quite likely there's something different. So we may have gone too far in lumping everything together. There's this kind of eternal war between the splitters who split fossils into many species and the lumpers who kind of lump everything in together. I would argue these are not purely philosophical debates. That, either there were a lot of species or there weren't. And I suspect in general, evolution tends to create a lot of species. And that, hey, it's why am I a splitter? It's not philosophical. It's nature is the splitter. Nature's the splitter. Nature splits one species into many, many species. It makes 10 million species starting with one. Literally, there's 10 million species today. So nature splits a lot. So I think to accurately capture that, taxonomists kind of need to as well. So are we underestimating dinosaur diversity? And could that potentially be distorting our understanding of dinosaurs? For example, we look and say at the very end of the dinosaur era, there's not many species when the asteroid hit. Well, maybe that's because we're not recognizing all the species that were there. I would suggest that dinosaurian faunas dinosaurs were very diverse. First of all, probably each of these faunas had a very high diversity and a surprisingly high diversity of large-bodied species, which might seem counterintuitive because we don't see that today. Well, yeah, but today is not really relevant. We live in the wake of the Pleistocene megafaunal extinctions. The Clovis people came in and wiped out all the mammoths. So we tend to assume that low large herbivore diversity and low carnivore diversity is normal. It's not. We live in a post-extinction era. We live in the wake of a mass extinction. What we see today is not normal. What we see in the liberated tar pits is normal. What we see in the Dinosaur Park Formation is normal. What we see in Old Divide Gorge is normal. What we see in the modern world is not normal for large vertebrate faunas. They should not be this depauperate. They should have way more species. So first of all, I think your average dinosaur fauna should have a lot of species in it. Second, based on what we see in dinosaurs, and again, you see this in African mammals, different areas have different species. They tend to kind of, one species specializes on this habitat and has a fairly small range, and this other species specializes over here. And we see this consistently in North American dinosaurs. These species don't have large ranges. What that means is, so first of all, you look at one assemblage, you go through there, you find a lot of species because it has high diversity. Then you move a few thousand miles away, you find a completely different set of species. So that's one reason we just find a lot of dinosaur species. And then the third reason, in addition from high standing diversity, high endemism, different things in different areas, is high turnover. Dinosaur species didn't last very long. Most of these species lasted maybe 1 million years, maybe 500,000 years. We know in the Hell Creek Formation, maybe it spans 1 million years, maybe not even that. And there's 2 species of Triceratops, one after the other, so maybe 500,000 years per species. And that's not extraordinarily high turnover. I mean, we split off from the Neanderthals evolved into separate species in a little less than 1 million years. So in 500,000 years, you can easily get a new species. So as you move through time, every 500,000 or 1 million years, you have species either evolving into new species or it goes extinct and something else comes in and takes its place. So there's a lot of turnover. So between these three patterns that we see, high diversity per ecosystem, different species in different ecosystems, these ecosystems turn over through time. There's just a huge number of dinosaurs out there. And I've done some back of the envelope calculations. It wouldn't surprise me if there were 100,000 dinosaur species in total, maybe 500,000. And the fossils we have, it wouldn't surprise me if we're dramatically underestimating dinosaur diversity. I think currently there's something like 700 or 800 species known. Could the fossils actually represent twice as many? It is entirely possible. So I just think it's kind of interesting that T-Rex is one of the most intensively studied and well-known species of dinosaur, but it's actually not one species, quite likely. It's a bunch of different things, and this suggests there's a lot of work to do on all the other dinosaurs as well. Last of all, kind of a parting thought on discovery. How do you discover things? And first of all, it's pretty amazing to be involved in the discovery of a new Tyrannosaurus. That is like a once-in-a-career thing, and it's an amazing privilege to be part of that. Not even once in a career. I'm lucky. Probably a lot of careers go by and you don't get to name a Tyrannosaurus species. So it's pretty unusual, and that's pretty cool. How did this come about? Remarkably, it didn't involve going to the field. I mean, at least not for me. Other people went to the field, which is great and awesome because then I have stuff to work on. And hey, much respect to those guys. That's a really important part of the process. But the discovery of the species itself and the recognition of new species didn't happen on the field. It happened in a museum in downtown Albuquerque, New Mexico. And not only did it happen in a museum, it wasn't even in some dusty back room in some crate that hadn't been opened in 100 years. This specimen was on display in the museum. You can see it here in the display case. So we had a new species and a new species of Tyrannosaurus on display in a museum, which might seem like, it might seem like the last place in the world you go to look for a new species. But there's that joke about the guy who robbed banks. And why do you rob banks? Well, that's where the money is. And it's why do you go to museums to find new species? Well, that's where the fossils are. So you go to a museum, right there on display, here's your new species. So sometimes discovery doesn't mean looking, doesn't mean new data. It doesn't mean new fossils. Sometimes it means questioning assumptions skeptically and seeing fossils and seeing the data with a new perspective. So that concludes our talk there. I'd like to thank you guys for listening. Thank everyone else on the team. It was great to be invited on this project and be a part of it and kind of help nudge this thing along towards producing an amazing paper. And thanks to everyone I talked to about discussions about the provenance of Tyrannosaurs and evolution and so on and so forth. And all right, take care.